Hi there. My name is Zachary Espiritu, and today I'm presenting time and space-efficient aggregate range queries over encrypted databases, work that I conducted with Evangelia Anna Marcato and Roberto Tomasia while I was an undergraduate at Brown University. The motivation for this paper starts in the cloud computing model, where the client wants to outsource storage and computation of their application to a third-party cloud service provider. There are many benefits to doing so, as shown on the slide here. However, privacy concerns arise, especially given that a significant amount of trust is given to the service provider in handling and preserving the security of the client's outsourced data. Such concerns have led to the development of the field of encrypted search algorithms, in which we have the same client and server, except we assume the client is trusted and holds some kind of secret key, and we assume the server is some semi-honest, untrusted server. The client can then use their secret key to upload their dataset in such a way that they can send queries and receive results from the server while still maintaining some defined privacy guarantees over their data. Now, there are many different types of encrypted search algorithms, some implemented with different kinds of techniques, and there are many algorithms for specific types of queries. The type of query that is most interest to us in this particular work is that of a range query. For example, suppose we have a shopping application that has an order table containing dates and costs of orders, and the client is interested in all of the orders purchased between July 11th and July 14th. There are many existing encrypted search algorithms for range queries, many of which use different techniques, but they all follow the same process as we just saw before. You use your secret key to generate some kind of encrypted query token, and then the server returns all of the encrypted results for the client to then decrypt. Now, despite the existence of many encrypted search algorithms to handle range queries, there has been significantly less attention drawn to another fundamental type of query known as aggregate range queries. In this kind of query, the client is not actually interested in the records that fall within the queried range, but rather they are interested in the result of an aggregate function applied to those records. In this example, we've modified the query such that we now are looking for the average cost of all the orders that fall between July 11th and July 14th. In plain text, this kind of query is simple to answer. The server can use whatever method it wants to retrieve the records, and then it can compute the aggregate client side and then send a single constant size value back to the client. In the encrypted setting, this is much more challenging. One might use an existing range query ESA to answer these kinds of queries. However, this incurs some additional overhead. While the client can still send a regular range query token and then send an encrypted table and then decrypt all of the records and then compute that average cost, the client is now incurring additional computation at the client side, additional bandwidth between the client and the server, and on the case of the server security and privacy, we might be revealing additional leakage to the server in that we are accessing multiple records, but even though we are only really interested in the single aggregate value. Now, there are many existing techniques that can be used to answer these kinds of queries. For example, expressive techniques such as fully homomorphic encryption, multi-party computation, and similar solutions such as hardware-based trusted enclaves can be used to achieve queries for any arbitrary type of aggregate function with high security guarantees. However, these solutions often incur substantial performance overhead that make them unsuitable for practical use. You can also use another type of homomorphic encryption called additively homomorphic encryption to be able to compute additive types of aggregates, such as sums and averages. While these types of homomorphic encryption schemes have better performance, they have reduced expressiveness and are not generic to other types of aggregate functions. You might also use other types of encryption, such as property-preserving encryption, to be able to support things such as medians and modes. However, these kinds of encryption schemes have been shown in prior works to be extremely vulnerable to inference attacks and are not suitable for secure applications. Given all of these concerns, we decide to turn our focus towards structured encryption, which is a class of techniques that allows the client to encrypt a data structure, such as an array or multimap, and outsource that encrypted structure to the server. In particular, we're interested in this kind of line of work because of the fact that in 2018, there was a similar paper by Demertis et al., in which they show exactly how to use structured encryption to design some preliminary schemes for sum and minimum queries, 2 schemes to be exact. In this work, we're interested in seeing how far we can generalize this technique to see if we can answer other types of queries and to see if we can improve on the performance bounds given by those initial schemes in this Demertis paper. To do this, we developed the following contributions. We first develop a framework known as ARC, which allows one to build encrypted aggregate range query indices for basically any type of aggregate range query one might desire, as long as there is a suitable plain text aggregate range query index that already exists. Using ARC, we're able to derive new constant time and query bandwidth schemes for encrypted range minimums, approximate modes, and approximate medians, and in some cases, improve upon the storage bounds already given in the Demertis 2018 paper. We also back up these results with a formal implementation and evaluation of these schemes. Our paper also concludes some other results that we don't cover in this presentation. To give a high-level overview of how the ARC framework works, the idea behind it is that the client chooses a plaintext aggregate range query scheme that they would like to have an encrypted scheme with the equivalent functionality. In this slide, we denote this scheme with pi. Then they choose a suitable structured encryption scheme that can encrypt the data structure that is output by one of the algorithms in the plaintext aggregate range query scheme. Combining both pi and sigma together into ARC allows one to immediately derive an encrypted aggregate range query scheme with the same functionality as the underlying plaintext scheme. The formal pseudocode and formal security definitions of ARC can be found in our paper, but what's important to note is that you can immediately derive the leakage definition of the ARC instantiation based off of sigma and pi together. So the security definition in a proof is generic to any possible combination of sigma and pi. Now, a focus of this work is not just to derive new schemes, but also to talk about exactly how we can derive these schemes in such a way that they actually produce reasonably secure schemes. For example, you can pick any plaintext aggregate range query scheme and plug it into this ARC framework. However, as we show in our paper, some plaintext aggregate range query schemes actually are more secure when you can put them in this framework in comparison to other equivalent schemes. In the paper, we formalize this intuition via a new definition that we call data obliviousness. At a high level, a data oblivious scheme might leak the domain size and information about the queries, but it doesn't leak any other information. In particular, it doesn't leak any information about the database size, such as the number of records, database distribution, or really anything about the data itself. The idea behind the data oblivious definition is that if the query distribution is independent of the data distribution, then all known data reconstruction attacks don't work against data oblivious schemes. And this is not from a computational perspective, but rather from an information theoretic perspective. As we discuss in our paper, this data oblivious idea is very useful in the aggregate setting because schemes don't result in the same leakage as more general structured encryption structures would. This is because of the fact that in some sense, the aggregate structures have reduced expressiveness than what you would see in the structured encryption structures because of the fact that they're only really returning a single constant size value as opposed to regular range query structures, which return accesses to multiple records, for example. In our paper, we go through several different types of aggregate range query types, and we talk about how we satisfy data obliviousness for each one of these structures. But to give you a sense of exactly what needs to happen for some of these query types in order to achieve data obliviousness, we'll talk about our work on one specific query type, which is minimum range queries. In the Demeritz's 2018 paper, they present two minimum schemes, their best one being a structured encryption-based scheme, achieving O n log n plus m storage, where n is the number of records and m is the domain size, with 2 round trips back and forth to the structure. In this paper, we present a new scheme called linear min, which achieves storage linear in the domain size, with 1 round trip at the expense of prohibiting certain small queries of size less than log m. Now, while this is a limitation on the functionality of the scheme, as we show in our paper, the scheme that we present satisfies the data oblivious definition, while the scheme in Demeritz's paper does not satisfy the data oblivious definition. And so under the data oblivious assumptions, we can achieve better security using our linear min scheme. Our linear min scheme is based off an existing scheme by a 2006 paper by Fisher and Hune. We don't have time to get into all the details of this scheme, but just to give you a high level of how this works, given a particular database, in this case, we have a database with size domain 16, you split up the database into blocks of size log m, and then you generate a sparse table structure over the minimums of each of these blocks, basically a structure that allows you to answer all range minimum queries that span entire blocks. And then to answer queries that fall entirely within a particular block, you then generate an additional lookup table that stores the answer to all possible queries that fall within a block. Then queries return a reference to part of the lookup table in a second round access. As we show in our paper, this lookup table component results in a scheme that is not data oblivious when you try to combine it with the ARC framework. Now, the reason why this scheme is not data oblivious is because of the fact that the lookup table returns different references to different parts of the lookup table if the underlying plaintext contents of the database have changed. This does not satisfy the leakage requirements of the data oblivious definition. To solve this challenge, we modify the scheme in such a way that we instead use a different lookup table encoding that stores the answers to all suffix and prefix queries of a block. As we show in our paper, this encoding satisfies the data oblivious definition while still preserving linear space storage overhead, though it does prevent the user from issuing subqueries of size smaller than log(n). However, as we show in our paper, there are some ways to get around this, and we invite the readers to look at our paper for closer details. It's also worth mentioning that this is just one example of a scheme that needed to be modified. In our paper, we show how for other types of queries, you don't always need to modify the plaintext schemes. And in fact, for the other two types of queries that we introduce new schemes for, we don't need to modify them at all, and they work easily and generally. To reiterate, in this paper, we present a new framework called ARC that allows one to build encrypted aggregate range query indices by combining structured encryption primitives with an existing plaintext aggregate range query scheme. Additionally, we define new definitions that are unique to the aggregate range query setting and show how those definitions can show us when a plaintext aggregate range query scheme is potentially suitable for a secure ARC instantiation. In the paper, we go into more details about our implementation and evaluation, as well as some other results in the appendix. Thanks so much for listening.